Okay, so the first transformation you should be looking at is the one that says horizontal shift. Can anyone tell me what direction horizontal is? Up, down, or left, right? Left, right. So on the inside of your foldable, you should see fx plus h. So anytime you are inside of a parent function, so if it's a quadratic, it's inside the parentheses. If it's an absolute value, it's inside the absolute value bars. If it's a square root, it's underneath the square root. And you have a number being added or subtracted, that means you are shifting left and you are shifting right. So in our case, I'm going to do two things. There's a case where we have a positive h, and there's a case where we have a negative h. This is kind of what you're filling in on the inside flat part. So the positive h is going to be kind of the opposite of what we would think. That means we are going to move left h units. So if I have a plus 3 inside of my quadratic function, that means I'm actually going to move left 3. If I have a minus 3, that means we would be moving right however many units. So the tricky thing about left right is you're always going to do the opposite of what it looks like. So in the case of plus, we're actually moving left. In the case of minus, we're actually moving right. The next type of transformation is the vertical shift. And that always happens outside of the parent function. So again, when I have inside, that means it's inside the parentheses. It's inside the radical, inside the absolute value bars. If you have numbers outside, that is when we're shifting up and shifting down. This one is not going to be one where they do the opposite. If you have a plus k, that means you are going to be moving up k units. And then if you have a minus k, that means you are moving down k units. So we have our shifts, left, right, up, down. A lot of you are probably familiar with this because you may have seen some of it in your Algebra 1 class. But again, like I've said at the very beginning, I kind of teach it like you've never seen it before. So up, down, left, right. The other two types of transformations that we're going to talk about today is going to be your reflection over the x-axis and your reflection over the y-axis. Big thing that you have to know for these is your x-axis is the horizontal axis and your y-axis is the vertical one. So in these cases, whenever we have a reflection over the x-axis, you're going to have a negative sign outside of the parent function. The notation that we use here just means any parent function could apply. Any function that you learned in your foldable, all 5, could technically have these transformations. And then the reflection over y-axis, it's on the inside. All of this information should already be printed in your foldable. Now, how we actually go in and how we apply them. So whenever you are going to reflect over the x-axis, you're going to change the sign of the y values. And I sometimes like to include a picture just so you can kind of see what's going on. If I have a plane, and let's say, and I'm going to do a dotted one, this is my parent function. This is a quadratic function. If I wanted to reflect over the x-axis, that means the y values are no longer going to be what they originally are. They change signs. So whatever was negative is now positive. Anything that was positive is now negative. So the dotted line would be the original. The solid line would be the reflection over the x-axis. Now for the reflection over the y-axis, you apply it almost exactly the same. This time we're going to change the sign of the x values. And usually we don't see this transformation a ton because a lot of the parent functions that we deal with have reflectional symmetry. Basically meaning if I take a quadratic and I reflect it over the y-axis and it's sitting at the origin, it's going to look exactly the same. But one that will not, just to kind of show you an example, kind of like what I did before, if I have a square root parent function, so in this case, this is kind of roughly what a square root parent function looks like, and I wanted to reflect it over the y-axis, it's going to change the sign of the x values. So everything that was positive is now negative. So anytime you have a reflection over the y, all you do is change the sign. Thing I want to make sure you make note of here, because I'm changing the sign, that doesn't mean that everything's turning negative. If it's negative to begin with, so if you think back to our cubics and our cube root parent functions from your foldable, those had some values where like -8, -2 was one of our key points. If I was reflecting that over the y-axis, those -8s are now +8s. So don't think of it as everything's going to turn negative, because in these examples they did. It's just everything that we start with is going to change signs. So positive to negative, negative to positive. Do I have any questions about the general rules of this? Okay, these are the only 4 we're going to talk about today. I'm not even going to fill in the information for the last 2. We will save those for the next notes. Let's go to the notes. Let's actually graph. Okay. A couple of things to point out. This is what it would look like if all of the transformations were applied to any function. To kind of show you what they could all look like. First, you could potentially have a reflection over the x-axis. Reflection over x-axis. So if you have a negative at the very, very front, that is a reflection over the x-axis. If you have a negative on the inside of your parent function, that is a reflection over the y-axis. Generally, and I will say as the person who mostly writes your notes and your tests and all of that, we don't give you both of them at the same time. We usually will ask you for one or the other. So if you see something and you're like, does this have both a reflection over x and a reflection over y? Most likely, probably not. Okay, and then we have our plus h, which is going to be our shift left, right. And again, I like to make a note. You're going to do the opposite of what this looks like. So if it's a plus, you're actually moving left. If it's a minus, you're actually moving right. And then our last transformation for today, this is our shift up, down. So if I had something with all of these transformations, which is what we'll kind of see today, I'm identifying them as separate things. So I'm not going to necessarily say them as like I only have one. You will identify all 3, or not really 4, but 3 or 2 transformations that you have. Big thing to remember, reflection over x-axis will change the sign of your y values, and reflection over the y-axis will change the sign of your x values. Just if you happen to not have your foldable handy, I like to keep that there. We will always start by graphing our origin and moving it. So I have a little disclaimer here. I know a lot of the graphing that you did in Algebra 1 may have been done in the calculator. Every single graphing problem that you do in this class is by hand. So that is why you have to know these key points. That's why I emphasize that filling out your foldable and having these points handy is important. When you sit down to take your test for this unit, you will not have these notes. You will not have these foldables. You are responsible for knowing this information. So when we go in and we practice this, I try to teach it in a way where you can recognize patterns and see that instead of having to like think of it super, super hard of like plugging it into a function, you know, like the quadratic pattern is 0, 0, 1, 1, 2, 4. And that is how we graph. So the first thing we do is we identify our parent function. So any guesses what the parent function for number 1 is? You can look at your foldable, see which one it looks like. What do you got? It is a cube root. So I'm going to write out cube root. I also kind of like to write what the parent function looks like originally so that I can come in and identify how is it different from that parent function. So looking at what the parent function is and looking at what I have, what is the noticeable difference between the two things? There's a -1. So that -1 that I have, is it inside the parent function or is it outside? It's inside. So anytime I have something inside, that is going to be a shift to the left or to the right. So this one is going to be to the right. Why is it to the right? It's the opposite. When you see -1, a lot of us want to think, okay, I'm going to the -1 number. It's always the opposite on the inside. So we're going to go ahead and we're going to say this is shifting to the right 1. Now, the second step of graphing is to shift your origin accordingly. This is the only transformation I have. The only thing I'm doing to this graph is I'm moving it to the right 1. So I kind of move everything together. So in every parent function, as you watch the video, it started off with points that began at 0, 0. 0, 0 is what I refer to as the origin, because that's kind of where all parent functions begin. And I'll kind of scroll up so y'all can see. The origin is at 0, 0. This is what we're shifting. So we just said that the origin is going to shift to the right 1. So I like to come in and I will usually draw like a little intersection where that right 1 and then up, down, depending on what we do, actually moves to. And I draw, as we kind of start learning how to do this, I draw a new y-axis and a new x-axis if we need it. This one we can use the same one that we have from the origin, but this is basically going to act as our new x and y-axis. Now the reason why I do this, I've done graphing, this is my 9th year teaching graphing overall. The best way to do it is to think of it as patterns. So even if you haven't filled in your foldable, bless you, when I have a cube root function, there were 5 key points that we have to have. So I'm going to write them out. 2, 3, 4, 5. A key point for every single parent function that we talked about was 0, 0. And so around that, typically we would have negative, oops, wrong direction. +1, +1, -1, -1. And these are for cube root. So if you look at your foldable and you go to the cube root page, I'm pulling the 5 points that were in column 3. So that is what I'm talking about. So I'm going to go in -1 cubed is -1. +1 cubed is +1. -2 cubed was -8. +2 cubed is +8. So these are the 5 points that if I had no transformations whatsoever for a cube root function, these are the 5 points I would graph. Now, I'm not doing anything to these points. They're not getting reflected. All they're doing is being shifted. So what we're going to do now, the way that we kind of graph in Algebra 2 Advanced, if you have methods that you learned in Algebra 1 and you're like, I know how to do it the way my Algebra 1 teacher taught me, that is fine. There's no bad way to do math as long as it's correct. But I'm going to show you how we do it. So this is the origin that we start off with without any shifts left or right. I'm going to treat this new intersection as my new origin. And so by that I mean that's going to become my 0, 0. So I'm going to have a graph point at 0, 0. And then the next point that I would normally have is 1, 1. So I'm going to go right 1, up 1 from that new origin. And the next point that we would have in a regular cube root is 2, 8. So, or cubic, sorry, I flipped these. Just kidding. Let's go back, change. This needs to be 8 too. cube root, not a cubic. This needs to be -8, -2. Fix it real quick before I even graph it. -8, -2. So now I'm going to go right 8 up 2. Now, right 8, I'm going to kind of highlight what I'm talking about. 1, 2, 3, 4, 5, 6, 7, 8, up 2, 1, 2. So this is where my next point is going to end up. So 1, 2, 3, 4, 5, 6, 7, 8, 1, 2. So all I'm doing is counting from that new origin point. So I went right 8, up 2. I went right 1, up 1. And then when I look at my other 2 key points for a cube root, that is left 1, down 1. So I'm going to have a point here, and that means I'm going to go left 8, down 2. So 1, 2, 3, 4, 5, 6, 7, 8, down 2. And then when you connect your dots, it should look like your cube root function that we drew. The only change to it is that it shifted every single point to the right 1. So this is why I really emphasized knowing those key points is important, because if you don't know the key points, you're not going to have accurate graphs. And when we check these graphs on your tests, we are going to check, is your point in the exact correct position? It's not going to be, oh, it looks like what it's supposed to be. It has to be at the right XY point. So that is why we really, really emphasize knowing these key points in the foldable. Now, one of the benefits and one of the reasons why I enjoy the cube root and the cubic is they have no restrictions whatsoever. You'll notice it ends in an arrow in both directions. So when I write the domain and I write the range, all real numbers, -infinity to +infinity. It does not matter what you do to a cubic or a cube root. You can reflect it, you can shift it, you can stretch it, you can compress it. It is still going to be all real numbers every single time. Okay, so this was one where it was just being shifted left, right. Let's go ahead and let's look at number 2. It says we got 2 things going on. First, what is my parent function? Quadratic. Quadratic. And so that means without any transformations, it would look like y equals x squared. Now I'm noticing 2 things going on. I have a +2 on the inside of the quadratic function, and I have a -6 on the outside. That's going to be 2 different transformations. What is the +2 telling me we're doing? Left 2. So we're going to go left 2. And you always do the opposite for that one. But for the -6, we're going to do what it looks like. What is the -6 telling me? Down 6. And just to remind you of the key points for a quadratic, there's 5 of them, like there was for the cube root. They're different. Always, always, always going to have 0, 0. 1, 1 is another common one. This one, if I take -1 and I multiply it by -1, what do I get? +1. A negative times a negative is a positive. So when I do 2, 4, I'm going to get -2, +4 as well. At the end of the day, in the video I mentioned, yes, I like for you to know these. It makes it easier. It saves you time. But at the end of the day, they're functions. You can take -2, you can plug it in. You can take -1, you can plug it in. You can take 0, you can plug it in. You can get these values without having to memorize them. So make sure you know them before test day. So now, I got my parent function, I got my key points. I'm going to take that origin, I'm going to shift it to the left 2, and I'm going to shift it down 6. And I personally like to draw these new lines so I can kind of see where would my new origin point be. So I'm going to treat 0, 0 as if it's at this intersection from this left 2 and this down 6. Now, from this new origin is where we draw our key points. So if I wanted to plot, quote unquote, 0, 0, that's going to go at the intersection of these two shifts. I always go positive first. The next point would be 1, 1. So I'm going to go right 1, up 1. And the next point for a quadratic is 2, 4. So I'm going to go right 2, up 1, 2, 3, 4. And another nice thing about the quadratic function is it has symmetry. It has reflectional symmetry, meaning the right side looks like the left side. So if you get one side of these down, you can kind of just mirror the other points on the other side of your graph. We're only ever going to ask you for 5 points total. So the 5 points that we give you in this foldable that we went over, those are the 5 points that you have to know. Those are the only ones. You can absolutely draw more if you want to, but this is the minimum we require. Yes?
You said from 1, 1, if you go right to up 4, or you only went right once, then you went on my 2.
No, I went right 2. From 0, 0. So it's always counting from 0, 0. Yep. So counting from 0, 0 is where we take all of those key points. Domain for quadratics is negative infinity to positive infinity. What is the lowest y value on this graph?
Negative 10.
On this, like where the graph ends. Negative 6. So the lowest point that I have included, and if you need to go in and kind of look at it the way we did when we were talking domain and range, it's like there's a filled in point here at negative 6, and there's an arrow pointing upwards and not stopping. So because there is a graph there and because there is a point there, we're going to have a bracket, negative 6. Will this graph have any restrictions? Like, will I ever have a stopping point as I increase? So that means it's going to go all the way up to positive infinity. So you will have to be able to identify domain and range of your transformed graphs as well. Any questions on the front page before we get into reflections? This is just shifting. Okay, let's jump to the back. Yes. Not right now, when I'm done. Okay, for the transformations, we have what kind of function here? Absolute value. Absolute value. If I had no transformations, it would just be an x in between two absolute value bars. And then we have 3 things going on here. We have a negative in front. We have a -3 on the inside. And we have a +8 on the outside. The order we apply these in is always going to be shifts first. So I'm going to identify those. The -3 that I'm looking at is a shift where? Right 3. And my +8. Up 8. So before I do anything with the reflection part, I shift my origin. And so I'm going to go ahead and go right 3. Oops, let's color coordinate a little bit. There we go. Right 3. And let's go up 8. And so this intersection is going to be my new origin. Now, the negative in front, it is technically outside of the parent function because it's not inside the absolute value bars. So anytime you have a negative outside, that's going to be a reflection over the x-axis. So if it's outside, it's going to be the x-axis. If it's inside, it's going to be the y-axis. And a little note you can make for yourself, this means we are going to change the sign of the y values. And I know we've mentioned this multiple times, but I try to include it on your examples. So when you go back and look at these, it can kind of help you figure out where we're going. Okay, so with that being said, key points for an absolute value. In the video, I gave you -2, -1, 0, 1, 2, because that's kind of what we use. Absolute value can technically fit a lot of different points on a 10 by 10 grid. So you don't have to use those all the time, but in this case, it fits nicely, so I'm going to keep them. Absolute value takes any number that you plug into it and it makes it positive. So when I take the absolute value of -2, I'm getting +2. When I take the absolute value of -1, I'm getting +1, 0, I'm getting 0. If I take the absolute value of +1, it's going to stay +1. It does not change. It's making all of your values positive. So these are the key points. If I had the parent function, no transformations, these are the 5 points I would have to graph. Now, we're not doing the key points. We are remembering that we're going to change the sign of the y values. So what that means is the x values do not change. So every time I teach this, I say if we know something isn't going to change, we write it out as if it's not going to be any different. So I'm going to come in, I'm going to do -2, -1, 0, 1, 2. Because the x values will not be any different than what they were for the parent function. The y values are going to make that change where the sign is going to be different. So currently, for the absolute value parent function, all of our y values are positive. So that means when I come in to graph the reflection over the x-axis, I'm going to take the negative of them. So this is going to be -2. This is going to be -1. 0 doesn't have a sign, so it's going to stay 0. This is going to be -1. This is going to be -2. And so when I graph this, I'm going to have 0, 0, right 1, down 1, right 2, down 2. And like quadratics, the absolute value has reflectional symmetry. So if you are able to graph one side of it, you can just graph the mirror image on the other side. And we should have an absolute value function that has been reflected. Yes?
Wait, I thought it was blank, because I thought it would be on the other side of the graph, not the top side.
It's going to be reflected after we've shifted. So it's still facing the downward direction, so it is reflected, but then it was like moved to where it needs to be. Okay, domain. Do I have any restrictions on the x values? No. -infinity to +infinity. And I will say the most commonly missed problem, kind of, in pair with something else, on this Unit 1 test is when we write a range that has been reflected over the x-axis. These arrows, they're pointing downward. When I have an arrow pointing downward, does it ever have any restrictions? No. So that means the starting value, the smallest number y could possibly be, is -infinity. And it's going to go all the way up, and it's going to stop at y equals 8. So that means I'm going to have an 8 with a bracket. If you have any point where your graph touches, it is going to be a bracket. It has to be included in either your domain or your range. Now, again, most likely when we ask you to reflect over the x-axis, it's going to be something where it makes sense. So maybe a quadratic, maybe a absolute value. The cubics and cube roots are kind of fair game, but reflecting something where you can visibly see it is now facing a different direction. For the last example we're going to do together. Question? Okay. For the last example we're going to do together, we're going to have a reflection over y-axis. So I have three things going on. I have a negative on the inside, I have a +4, and I have a -5. So again, shifts first. So that +4 means we're moving to the left 4. And that -5 means we are moving down 5. So I always come in and I shift accordingly. So we're going to the left 4. And we are going down 5. And this intersection is going to be treated like it's our new 0, 0. So once I have this, what is the parent function of this particular graph? Square root. So I'm going to have a square root. I forgot to fill that in. And the nice thing about square roots, we don't make you do 5 points. We only make you do 4. And that's why in the notes we didn't talk about a 5th point. The 5th point can sometimes be too big because the next perfect square would be 16, and that sometimes doesn't fit the way we want it to. So for square roots, it's 0, 0, 1, 1. The square root of 4 is 2, and the square root of 9 is 3. So we only will ever require 4 points for these kinds of graphs. Now, before I do my reflection, I'm going to identify it. This is a reflection over the y-axis. And we apply it by changing the sign of x values. And so when I change the sign of these x values, that means the y value is going to stay the same. So I'm going to go in and I like to fill in the values that do not change just so that I don't make an error and change something that I'm not supposed to. So the 0, 1, 2, 3 are going to stay the same because we're not changing y, we're changing x. And then I'm going to take the, which this may not fit perfectly, but we'll fit as many as we can on the grid. I'm going to take the x values and I'm going to change the sign. So this is going to be 0, -1, -4, -9. I think we'll only be able to fit 3. I'll make a note to fix it next year. Okay, so let's go in and let's change these signs. I'm going to have a point at 0, 0. Now, the new point that I'm graphing is -1, +1. So that means from 0, 0, I'm going left 1 and I'm going up 1. So I'm going to have a point here. And then I'm going left 4, 1, 2, 3, 4, up 2. And technically, even though it's not going to fit, we would go left 9. I'm going to try to estimate where it would be. 1, 2, 3, 4, 5, 6, 7, 8, somewhere here. And you should get a square root function that looks like it was flipped over the y-axis. Now, the square root function is the most restricted parent function you will see. When I do domain, the arrow that I'm looking from left to right, it's on the left-hand side, so that means it's going to -infinity. What x value does it stop on? -4. And we always have a bracket because it's included. Now, the y value has a starting point and it's kind of moving up. The first y value we encounter is -5. And then do I have any restrictions after that? No. It's going to go all the way up to +infinity.